Hello everyone, welcome to my video. In this video I'm going to talk about audio dispersion. This video is made for our computational physics class of fall 2021. In this video I'm going to talk about some basics of wave, Fourier transform, and an example using Phyphox and Jupyter Notebook. I hope you like it and enjoy it. So let's get started. To explain audio dispersion I need to talk about waves. In this video I'm talking about mechanical waves. Example of mechanical waves could be sound waves, or waves in the water, or waves in a spring. The equation of a traveling wave, which is traveling through the medium, could be written as follows, where A is its amplitude, K is its wave number, and omega or W is its angular frequency. The speed of the wave at which it propagates through medium is given by omega over K. Here is a simple example. Suppose we have a wave y1 where amplitude A is 1, K is 1, and W is also 1. This is how it looks like. Let's y2 is another wave which amplitude is same, A is 1, W is also 1, but K is 3 instead of 1. If the both waves travel together, this is how their wave is gonna look like. This is the plot of those waves in the Desmos graphing calculator. So when I plot the y1, the waves moves like this. Here A is 1, K is 1, W is 1. If I plot y2 with K is 3, W is 3, and A is 1, this is how this wave is going to move. When the both waves travel together, this is how they are going to move. Notice that the wave function doesn't change because they both have the same wave velocity, which is 1 and 1 for both of them. But if I change the wave velocity for one of them, let's say for y2 I change the w's value from 3 to 1, and we see dispersion. The wave function changes as it moves. This is because the velocity is not same for both of the waves. This is an example found in nature. When a boat passes through water, it creates waves, but not all of the waves have same velocities, which causes the dispersion in water wave, what we see in this video. My next topic is Fourier transform. This is the tool I'm going to use for my example. Fourier transform breaks down any wave into a sine or cosine as a function according to their frequencies. Basically, it converts the information from the time domain to the frequency domains, which gives us a different view of the signal. Using Fourier transform, almost every imaginable signal can be broken down into combination of simple waves. Could be a function of sine or cosine. There are two kinds of Fourier transform that we use in computation. One is DFT, which stands for discrete Fourier transform. Another is FFT, which is fast Fourier transform. So even they both serves the same purpose, there are a lot of difference. The Fourier transform performed on a signal within a finite range is called discrete Fourier transform. The mathematics and the algorithms of the Fourier transform are the heart of discrete Fourier transform. The first Fourier transform is just a modified algorithm which is faster. This is just do the same task as discrete Fourier transform, but it takes very lower number of steps, which makes it faster and calculate a huge number of transform. So the first Fourier transform is nothing but the implementation of DFT, but the FFT provides a more efficient result than the DFT. and the computational time required for a signal in the case of FFT is much less than that of DFT. My next topic is Phyphox. This is the smartphone app that I'm going to use to do the experiments. Phyphox has varieties of experiments which uses your cell phone sensor, and you can do a lot of physics experiments with this. Within the Phyphox X, I'm going to use audio amplitude to do my experiment. This experiment allows the app to take the audio data by using its microphone and then export the data as a CSV file later, which we can use for our experiment. So for this part, I'm going to use the Jupyter Notebook and take FFT for the audio data that has been taken with the Phyphox app. Using the Phyphox app, I have taken sounds of waterfall. So I let the tape run for almost 1 minute. I let that app record the data for almost 1 minute, and this is how this audio spectrum look like. So this one plotted the sound pressure level versus time. This is the screenshot from the app. The Firefox allowed us to export the data in CSV file, which I did, and then I uploaded for this notebook here. I used pandas to import the audio data, and then I have plotted it here as seems like same as the original one, which was on the screen of the app. Then I have used some code to take the Fourier transform, and this is how it looks like in Fourier domain. As you can see, we have lots of different frequencies here, almost 0.001 to almost 1000, a little above 1000. Okay, now I'm going to put a threshold value. I'm going to erase some of these noisy signals. So what I'm going to do, I have put a threshold value at 0.2, which is over here. This is 0.1, very close to here. So I'm going to remove all these values below that 0.2 and only take the values that above 0.2. So after this filter, this is how it looks like. So that's the all reds are the original values. This green is above this threshold value which I put at 0.2. So now if I compare the original signal and my filter signal, this is how it's going to look like, which is very clean. Yeah. That's all for today's video. Thank you so much for watching.